Aloha and welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs that's offered by a team at the University of California, Santa Cruz. We offer free public experiential learning sessions several times a month, featuring professionals from a variety of disciplines. You can scan the QR code on the screen for more information and to register for upcoming events. In this session, we have the privilege of shadowing scientists at the CHARA Array. Now, each telescope of the CHARA Array has a light collecting mirror 1 meter in diameter. The telescopes are dispersed over the mountain, Mount Wilson, to provide a two-dimensional layout that provides a resolving capability of a telescope with a diameter of 330 meters, or 1/5 of a mile. Now, the array is capable of resolving details as small as 200 micro-arcseconds, equivalent to the angular size of a nickel seen from the distance of 10,000 miles. Now, in terms of number and size of its individual telescopes, its ability to operate at visible and near infrared wavelengths and as long as baseline of 330 meters, the CHARA Array is arguably the most powerful instrument of its kind in the world. Now, in this session, it will feature an engineering program that includes upgrades to the MIRC-X beam combiner. We'll find out what that is very shortly. Now, not only will you get an introduction to the CHARA Array and astronomical interferometry, but you will also get to see live data collection from the 6 1-meter telescopes of the array. All right, let's go over to our guide on this extraordinary cosmic journey, Nick Scott, who is a telescope systems scientist for CHARA. Welcome, Nick. Thank you for inviting us to shadow you and your colleagues.
Thanks, Jamika. Thanks for the intro. Yeah, and thanks everyone that can be here. I'm going to share my screen and kind of dive right in. In the conference room, you should also see we have our guests and also one of the CHARA staff scientists, Cyprian Lantherman. Cyprian, wave. Maybe.
Oh,
I think
video
the video is frozen in the conference room.
Oh no, CHARA
Let's see if they can fix it. Well,
okay.
He was in the back of the room. We'll come back to him. And also I'll walk around with my laptop and introduce you. And we're in the control room here.
Sounds good.
So I'm going to go ahead and share my screen and start talking to you about CHARA. Let's see, we'll come back to that. Great. Okay. So this is a kind of a nice intro. This is one of our telescopes. This is a nice panorama. We're actually overlooking Los Angeles. This is the historic Mount Wilson Observatory. So there's the historic observatory, and then the CHARA Array is one of the tenets of the observatory, and we're doing active science here with the array of 6 telescopes. At the bottom here is our list of our consortium. So every one of these are some of our partners. I'll talk a little more about them in a moment. And this is one of our telescopes here opened up, a nice shot of it. So first off, who am I? Why am I talking to you? I started out in photography and film before getting into physics. I got really nerdy about cameras and wanting to know how they worked. And if you get too nerdy about how light works, you end up a physicist. So I went to University of North Carolina at Charlotte. I did an undergrad in physics and psychology, and I did astronomy research while I was there. Something that no one really told me while in undergrad until way too late, and I share it with everyone when I talk to the public. If you do grad school in STEM, there's a good chance if you do well that you can continue in grad school for free or even being paid. You were an employee as a grad student. So the head of the department, came to me and was like, Nick, what are you going to do now? And I'm like, I don't know. I'm out of money. And he's like, stay here. We'll pay you. We'll waive tuition. So that got me doing a master's in applied physics. I worked in biomedical optics and medical physics, and I also did some astronomy research and did a thesis on astronomy while doing medical physics classes and biomedical research. And I had a teacher who had Hal McAllister give a talk, and he talked about this thing called the CHARA Array, and he said, you should check this out. It's really cool. And I kind of got sucked into coming to Georgia State, thankfully, working exactly what inspired me to do it. The CHARA Array is a really incredible place. While at Georgia State, I went to a instrumentation summer school in the Canary Islands, and I also did what's called a co-tutel with Lucia at the Paris Observatory in Moudon. So got to spend quite a bit of time in France working because one of our consortium is the Paris Observatory, and I worked on a beam combiner, and I'll explain what that is later, there. And during that, I also came to CHARA. I worked as an operator while finishing my PhD. That's here in LA. And then did a postdoc at NASA Ames, working on exoplanet characterization and validation, building instruments, which is I'm at Jamaica, was our speckle instruments at Gemini North. So we have Gemini North and Gemini South has some of our speckle, which is another type of interferometry. But I came back to CHARA when the position opened up, and I've been here for a few years now. Early research I did was biomedical optics, astro on variable stars, planetary nebula, and building these medical devices. And here is a laser used to break up a kidney stone. So putting high power light into lasers and using that for medical devices. So kind of a different scale than astronomy. These are the speckle instruments. This is some of the team. This is Steve Howell. And this is the Gemini North telescope. So this is our tiny little speckle camera that is incredibly popular and working really well, still going strong at Gemini North and Gemini South. This is Gemini South here. This is this is Steve and Rachel Madsen. So came back to CHARA. I mentioned the consortium. So Georgia State built the CHARA Array with funding from the National Science Foundation and originally built a 2-telescope classic beam combiner. So just 2 telescopes at a time from the 6. And part of what's worked out really well for us, science is all about collaboration, building up this consortium. So every one of these institutes, University of Michigan, Exeter, Côte d'Azur, Sydney University, all over the world has contributed something that's a major milestone for the array. And that's really worked out well for us. So either new instruments that do focus on a certain type of astronomy or new technologies or other driving science. This is a really lovely picture. This is what we call S2. So this is our south arm of the interferometer, our second telescope, which is the closer ones. And we kind of named them backwards. The ones that are far away are the 1 telescopes. The ones that are close in are the 2 telescopes. I'll show a map of that later. So the planning for the array started in 1985, studies for it in the 90s. Georgia State got $5.6 million to build a 5-telescope array in the mid-90s, and the NSF invested even more. And then we got another $1.5 million from the Keck Foundation to build the 6th telescope on the basis of doing better imaging. So really, it's worked out really well for us, and it's something that we hope to continue. Because as you can see, this is all more than 20 years ago that these original funding happened. So first fringes were in 99, and then in year 2000, we got fringes on the 331-meter baseline, making us the longest baseline ever achieved by an optical interferometer, and we still stand as the most powerful angular resolution observatory in the world. And this is some of the people I'm very lucky to get to work with. As you can see, it's a pretty small staff. Only 16 staff members are on site, and that includes, site managers, people that actually, do the hard work of, wiring the electrical and plowing the roads and keeping everything running. Our business manager in Atlanta, our director in Atlanta is Doug Geis, and then our director on site is Gail Schaefer, who is on this call. Hi, Gail, please chime in if you want to say anything. And then, the rest of all the people that work here. So first off, I want to talk about what it is to be an astronomer and kind of how it's changed. Because when you say you're an astronomer, this is what people picture. They picture you looking through an eyepiece, some historic. This is actually just across the parking lot. This is the 100-inch. They have a viewing tonight. So it's kind of a weird sight to be so close to LA, have this giant historic telescope that Hale and Hubble and Shapley used, operating still for public viewings right next to us while we're doing this cutting edge high resolution stuff. But this is kind of where interferometry, stellar interferometry was born and applied. So this is what we picture. This is more modern astronomy. This is Mauna Kea, very close to where Jamaica is. This is actually the Gemini base station in Hilo. This is different seasons of Mauna Kea. So this is modern, large single aperture astronomy. So these are the big modern telescopes. And this is what one of those looks like inside. And for scale, you see this is a cement truck. This is the telescope inside. This is me standing under the Gemini. I think that's Gemini North this time. Gemini North and South are twin telescopes. Sometimes you can't tell which one you're at. So this is kind of the cutting edge technology. And this is, it's beautiful inside, exactly what you'd think if you think of like modern astronomy. But we're going to go back a little bit. So Fizeau in 1850 and Michelson in the 1890s are kind of the two big names of the invention and application of interferometry. And in 1920, Kira Mount-Wilson with the 100-inch telescope with this outrigger, this 20-foot interferometer on top, works just like outriggers on a boat or like training wheels on your bicycle. It makes it wider. So the wider your mirror or lens, the smaller the details you can see. A way to remember this or tell it to your kids is, a hawk has really big eyes because it hunts really tiny things from far away. The bigger your eyes, the smaller the details you can see. So the eyes of the telescope, the aperture of the telescope determines the resolution, the angular resolution. So how small the details. So if you want to make an even bigger resolution, greater resolution, you put these outriggers on. And that's what Michelson did in 1920. He, with Pease, measured the diameter of Betelgeuse. So this is the first time that a star other than the sun had its diameter measured. So how big are the stars? And this technology was carried on by Brown and Twiss with these other types of interferometry in the 50s. Still have this thing called intensity interferometry. We'll revisit that if we want to talk about it, but I'm kind of stick to optical interferometry for now, but some people might be familiar with this experiment. So I said interference and interferometry, and I'll talk interferometric imaging. All it is building off the property that light is a wave. And when you have a wave, you have it can constructively and destructively interfere when the waves cross each other. And the way that shows up is you get these kind of bands of light and dark. And that's what we're doing is the star is giving off, the star is kind of like a point source. When you look at the stars at night, you can't see them as a disk, you see them as a complete pinpoint. They're as small of an object as you can imagine. And they're giving off a spherical wave of light that goes off in all directions. And that travels all the way through space, gets to Earth, gets all bent up in our atmosphere, but eventually comes to your eye or comes to your telescope. And if your telescope is big enough, you can resolve it as a disk instead of a pinpoint. And what we can do is take the light from multiple telescopes, combine it, and measure this pattern. And the size of this pattern, the contrast of these fringes and the size of them tells us something about that source of light. So that's why we call it interferometry. It's the science of studying this interference. And what it lets you do is get this angular resolution as if you have a giant single telescope, even though you're only sampling it like a cookie cutter of this big mirror, because that would be way too expensive to build a 300-meter mirror. So you can get the resolution, but not the sensitivity. So you may be familiar with like extremely large telescopes. I will make one dig at astronomers that we're not great at naming things. ELTs are extremely large telescopes. TMT is the 30-meter telescope. GMT is the Giant Magellan telescope. And then luckily the LSST was renamed for the Vera Rubin telescope. So actually naming it for a person instead of a silly acronym. The VLT I might mention is the Very Large Telescope. The OWL was a project, is just a cost study. OWL was the overwhelmingly large telescope. So don't ask astronomers to name your kid.
No.
So ELTs, there's two reasons to build a big telescope. One, I mentioned, I talk all about angular resolution, seeing the small details. The other is they work like a rain bucket. The bigger your bucket, the more water you catch. Well, the bigger your telescope mirror, the more light you catch, the more photons you catch. So the ELTs will be to go very, very faint. And they also will get high resolution. But even the biggest ELTs are the size of our smallest baseline, our smallest distance between two telescopes. So ELTs will be 16 times sharper in resolution than Hubble, but CHARA is already 17 times sharper than an ELT and way better resolution than Hubble. To be fair, I will say that the 30-meter telescope will be 150 times the collecting area. So they'll be able to go way fainter than us. That's our limitation. But we're trading sensitivity for the detail. There's a lot of text, but basically I just wanted to define, I may say arcsecond. What is an arcsecond? You may know, it's a measure of angle. So you may know that angle is measured in degrees or radians. An arcsecond is a subdivision of an arc minute, which is a subdivision of a degree. So there's 60 arc minutes in a degree, and there's 60 arc seconds in an arc minute, which means there's 3,600 arc seconds in a degree. So for comparison, here's like if you hold your hand up at arm's length, you hold your pinky up, your pinky nail is about 1 degree across. The moon and the sun are about half of a degree across. So that's about 1,800 arc seconds. I may also mention milli-arc seconds. So that's 1,000th of an arc second. So the full moon is about 1.8 million milli-arc seconds. Units are sometimes confusing, but just to give you an idea, 1 milli-arc second is a $50 coin seen at the Eiffel Tower from the Washington Monument. So we're talking really, really tiny. This is way beyond what you may imagine being able to see. And we're starting to get close. If we put telescopes far enough away, we could go into micro-arcseconds. So this is a millionth of an arc second. So that's the size of a period at the end of a sentence on the Apollo mission manual left on the moon. So astronomers can also be like kind of obsessive people. When you get into interferometrists, we're really obsessed with detail. And just to give you an idea, like this is the moon to scale. This is many people interested in astronomy have probably seen this image. This is the Hubble Extreme Deep Field. They had the brilliant idea of, hey, we've got this great new Hubble telescope. Let's look at a spot in the sky where there's no stars. What's the darkest spot on the sky and what's it look like? So they looked at this. The moon wasn't actually this close to it. This is just to give you an idea of how tiny a bit of sky this was. No stars, and just integrate. Just leave the shutter open, let the camera collect light. And this is the image they found. And this looks like a whole bunch of stars. But actually, each one of these dots is a galaxy. So space is full of stuff, full of stars, full of galaxies. This is one of my favorite XKCD comics. If you put this image on your phone and make this little tiny circle, there's 50,000 galaxies in that circle. If you have an old iPhone, the pixel's about 1/3 of a millimeter. If you hold that out, there's about 1,400 galaxies in the size of that 1 pixel of your phone. And if you put in the number of stars per galaxy, that means there's like 140 trillion stars in that 1 pixel. Can't see them all because they're too faint, but just space is both very, very empty and also full of stars. Kind of a contradiction. Okay, now that's kind of set the stage. We're going to talk about detail and stars and sizes of stars. This is CHARA and Mount Wilson Observatory. So the historic sites are this 60-inch telescope, this 100-inch telescope, and the 2 solar towers. So this is over 100-year-old observatory. CHARA is interspersed in here, and I'll show an image that there's 2 telescopes here, 2 telescopes here, and these 2, and then a lab back here. And the array, together, there's 6 telescopes because they're spread out, can see 200 micro-arcseconds, the size of an angular size of a nickel from 10,000 miles away. Or another way to put it is like from LA, we could read newsprint in Atlanta. So this is the site here. You can see LA, a little bit of Catalina, I believe. These are the 6 telescopes. And then the X is where I'm at right now. We're in the office here. This is to just give you an idea of the different telescopes. I talked about a bunch of them. I talked about the 30-meter telescope, the Gemini North telescope. This is a comparison of the size of some of the largest telescopes. This is the European ELT that's being built, the Giant Magellan telescope. Here's a basketball court for scale. Here's a human. Arecibo is this big white circle that barely can see part of the curve. So I took this image and I scaled it down to put CHARA on here. So CHARA, if you just trim the baselines, our mirrors aren't very big, but this is it. These are all telescopes that are 2 meters or bigger in the world. Let's see CHARA actually to scale. So here it is zoomed out. This is that same image. This is the size of CHARA from above. These are our 6 telescopes. That gives you an idea, even compared to these giant telescopes, how big we are. So we're simulating having a mirror That's basically the whole mountaintop. So every connection between the different telescopes is what we call a baseline. And each one of those gives us something that can be combined into making imaging. The more baselines you have, the better your image. So you can see it makes a whole bunch of triangles. That tells us something that's important. And this kind of tells us based on what color of light we're looking at, what kind of resolution we get. But this is the stuff that interferometrists look at. So I put this to scale here. That's that, single aperture. This is a comparison with, here's CHARA compared to, there's a couple other operating interferometers in the world. The main one is called VLTI, the Very Large Telescope Interferometer. So they have some large apertures, and then they have these small telescopes that can move around to combine light. And then as far as what's operating, there's a large binocular interferometer where it's two telescopes that can be combined in Arizona. And then this one's closed, and there's what's called INPOI in Arizona, which is a kind of a smaller, another similar type of array. So we're there's us in the northern hemisphere and VLTI in the southern hemisphere, and that's pretty much it for big interferometers in the world. And a lot of people ask, well, why do we have two telescopes? Why are Gemini North, Gemini South? Why do we have an interferometer in the north and in the south? Because the northern hemisphere and the southern hemisphere look at opposite parts of the sky. Stuff that's very south, you'll never see in the north. Stuff in the north, you're never going to see in the south. That's why they have a different sky to look at. And you can argue over who gets the better sky. Better view of the Milky Way in the south, but there's some stuff in the north that's pretty nice to look at. So here's CHARA to scale. Here's that same image. What we're looking at doing now, and I'll talk a little bit about, is expanding our array. We have some sites where we could connect another telescope that we've made, a mobile telescope that can expand this out and make us even bigger. So we're looking at doing 600 meters or even 1100 meters. So this would give us 3 times better resolution than we have now. So even finer details. So this is the type of stuff that was cutting edge what we're working on. So this kind of sums it up. This would be our, over a kilometer baseline. So it's just incredibly large interferometer. And this would be a really, really interesting thing to have. So I'm going to try and show you now how the array works. This is a cartoon of where we're at. This is the office where I'm talking to you from. This is our beam combining lab. So all that light has to be brought together somehow. And it's a really long building, and I'll show you why it has to be so long. We have a machine shop on site. We have some residences so scientists can come and visit and spend the night while they're staying, while they're taking data. And then we have these tubes between all the telescopes. So we actually put the light into vacuum pipes. Second. So there's that mirror. Our shortest baseline is 34 meters. And then we have all the combinations in between. So this is one of our telescopes. Like Jamika said, it's a 1-meter telescope. So that's the diameter of the mirror at the bottom here. This is it with the cover closed. It's built to be really rigid. It's a really stiff telescope because vibration will really destroy your chance at doing this type of science. And this is it up here. You see these tubes coming out of it. The light comes in from the top, bounces off a secondary mirror. This yellow is the path of the light, goes off to the side, goes through what we have an adaptive optic system. So we try and make the light a better quality because it's messed up by the atmosphere. Goes all the way down, goes in what we call the crypt in the basement of the telescope, and it goes through a window and into the vacuum. And we put it into vacuum because the air is turbulent and we don't want it to mess up the light because all the wavy lines, right? Wavy changing of the wavefront. What I always picture is like you ever fill your car with gasoline and you see kind of a vapor or like see a mirage, you see the light gets all bent up. The atmosphere is doing that all the time to light going through it. So we put it into vacuum to prevent all this turbulence because it's going along the ground where different heat and cooling will cause the light to bend around. So we have an adaptive optic system at the side of the telescope. So most large modern telescopes have this. It's a mirror that can change shape and a camera. And the camera measures, you see this kind of waviness. It measures how turbulent the atmosphere is. And then it takes that mirror that's got a bunch of little push and pull rods on the back of it and cancels out that movement. So it does the exact opposite of whatever. If the light goes this way, it moves the mirror to bring the light back. And it does this very, very fast, many, many times a second. And then cleans up in the image of the light goes from looking something noisy like this to a nice smooth dot if everything's working perfectly well. So we clean up the light, put it into the vacuum, and then we send it on to the lab. So it comes through this vacuum pipe, comes up a periscope, and then goes all the way down this long room. And at the end of the room, there's a cart. And this cart moves throughout the night. Oh, I see a hand up. Oh,
Oh,
pause there.
excellent. Thank you so much, Nick.
Yeah.
This is absolutely fascinating. So I have a question from Jim. So Jim asked, it's not a problem that Chara is so close to LA with all of the light and air pollution?
Sure. Sure. That was a great question. Um, there's a few things you want in an observatory. You know, people often ask, why are astronomers traveling and going north to south for different skies? One reason, but another is happens that the best place to put your observatories are on a mountain, near the ocean, in a desert. LA hits some of those pretty well. LA, Mount Wilson is actually on the continental US, has some of the best seeing. And when astronomers says seeing, they mean the quality of the atmosphere. So good seeing means the atmosphere is like it's not there. It's very, very transparent and not turbulent. You want it to be very smooth. Now, continental US, Mount Wilson's got some of the best seeing. Better place is Mauna Kea. Mauna Kea is 14,000 feet up. Best place in the world. It's it's closest to like a sacred place of astronomy. It's what every astronomer wants. It's 14,000 feet up. It's very, very dry. And there is nothing around you except ocean, which means the air is moving very smoothly. And it moves and it hits that shield volcano and just barely moves. So you get the really good seeing there. So for LA, we don't have that, but we are near the coast. We are pretty dry, and we're at 5,700 feet. So we're pretty high up for the Sierras. And so that helps us. We have pretty good seeing, like we get arc-second seeing here. The other is we get a marine layer that comes in. The marine layer is a thick layer of clouds, and you can pretty regularly go outside at night when we're observing and see the Milky Way. Even though I'm about 40 minutes from LA, I can still see the Milky Way, which is really, I don't know of many places with this many high population that you can still see the Milky Way. But for us, it depends also what waveband, what color of light you're looking at. We have some instruments that work in the visible, but the majority of ours are near infrared. So H and K band. So in H and K band, you're actually glowing like a light bulb because we're warm-blooded, we have temperature, we're glowing in the near infrared. So for us, the sky brightness of the lights in LA doesn't affect us as much. The bigger thing is the camera, the optics, they're all warm. So the camera, though the optics are warm, the cameras, we actually have an Adur, or some of them are cooled by liquid nitrogen, or they have cryo pumps that pump helium through them to cool off the detector. So we keep the cameras very, very cold because we're observing light that comes from warm things. So that way LA doesn't affect us too much. Still not perfect, but it's pretty good. Any other questions before we move on? Everybody with me so far? We're still traveling with the light from the telescope. It's a big beam. The telescope actually doesn't bring the light to a focus. It just makes it a smaller beam. So we've got a beam that's about 12.5 centimeters of just collimated light coming from the telescope through all these tubes up to these carts. So every telescope has a clock drive in it, where to compensate for the Earth's rotation, you have to have the telescope move the exact opposite. So even for the past 100 years, telescopes have a clock drive that mechanically keeps it opposite of the Earth rotation so you can stay pointing at your star. For interferometry to work, you have to have not just the pointing of the telescope right, you need to make sure that the distance the light travels through your optical system is exactly the same. Okay, that would be easy if you're pointing straight up. Well, if your star is over here, the light's going to hit this telescope first, and then it's eventually, very quickly, but still going to take some time, hit the other side of the mountain. So that's what we call delay. We need to delay the light from that first telescope so that it does something else until the light from the second telescope can get there. So how do we slow down light? We can't change the speed of light, not easily. Definitely can't speed it up. We can slow it down, but the easiest thing to do is give it more distance. So that big long building, the main purpose it serves, and this is looking down at here, is to delay the light. So the light from the telescope that was hit by the telescope that got the light first, we take that light and we make it travel further. And we measure the position of these carts with another laser with a whole tracking system. This thing is actuated, it's got vibration dampening, it's got a bunch of different technologies built into it. And by the time it leaves this cart, the distance the light has traveled is exactly the same to a fraction of a millionth of a meter. And then it's okayed. I feel like it's like Willy Wonka's chocolate factory. It's gone through this stage and this stage and this stage, and now it's ready to like the chocolate stage. It's going to the beam combiner. So we get the path equalized. And if you don't do that, you won't get interference fringes. Interference happens when light travels the exact same distance and the waves overlap and you get constructive and destructive interference. So the carts do that for us. After the carts, we go to this area. Looks super complicated, is super complicated. I tell people that these optical benches, you see all the holes drilled in it, see all these devices. The coolest thing about doing like hands-on optical work in a lab is you get to work with really expensive Lego sets. You can buy and make these parts. You can move the lens or the mirror where you want it, and then you bolt it down on the table. So this is a really big Lego set, and the light comes down here. These black octagons look like stop signs. They're another kind of telescope. We take the light from 12.5 centimeters and we shrink it and we make it a 19 millimeter beam, so a little less than an inch. We do that for two reasons. One is that we need to fit in a lot of stuff in a close area. So we're starting to get smaller and smaller as far as how far we're traveling stuff. And then we also, cheaper optics that are smaller are cheaper. We don't want a bunch of big mirrors and we can't get them close together. So we shrink the optics down. So now we've got this this light coming off this mirror at 19 millimeters. In this area, you can't see it here, it's not in this picture. We have another adaptive optic system. Because we've had all these reflections, the light's gone. Every time you bounce light, it's not going to come off it perfect. So we take it through another system, another special mirror that can deform and change its shape, and we get the beam prettied up for us. And then it goes off either this optic or this optic. And these stages move back and forth. And this is what I tell people it's like switch yard for trains. It's an optical switch yard. The visible light goes off the first, it's called a dichroic, which just means it's like a half of a mirror. Part of the light reflects, part of it goes through it. And part of it goes off this. This is just a mirror. So the visible light goes this way, and the infrared light goes this way, and all goes to this other room where all the instruments are. So by the time the light leaves here, it's all gone the exact same distance. It's shrunk down to a more manageable size, and we've separated it into visible and infrared. And depending on which instrument you want, you can take any telescope to any instrument and any type of light, anything. It's all sorted out that way based on whatever science you want to do. And this is just a little schematic of the lab AO. So this is an optic diagram. So you see it's kind of complicated, but really it's just the same sort of thing of measure the light, see how turbulent it is, and cancel that out. And there's code and technologies to help us do that. So this is what I just described. The light gets bounced off. The blue is the visible, the red is the infrared, goes this way. And then it goes to our last room. Every one of these tables is a different beam combiner. And a beam combiner you can think of as a camera. This is the final stop. The light gets brought together, interfered with itself, so the waves are overlapping in some way and they causes constructive and destructive interference that we can measure, and they're brought to a detector. Some of them, they're interfered, then they go to a detector. Some of them overlap directly on the detector. Different reasons for doing different ones. And then this is kind of the layout from above of we have what's called MERC-X and Mystic. MERC-X is what we're using tonight. That's the first one on the table here. Chariot, it's one in the back. Cimmeril, it's this one. Pavo, it's from University of Sydney. And then we have some stuff to help us with alignment. And then the way in the back, we have Spica. So this is our French colleagues have built Spica for us. It works in the visible. And this all these lines are where the light goes. So either goes all to this table, or this table, or we could put in a mirror and direct it down here to this table. But GSU and the NSF paid for just this one combiner called Classic. And then all of our partners and everyone that contributed brought in these other instruments. So it's another way that University of Michigan is involved, and the Paris Observatory is involved, and Sydney, and all of these others. So this is super busy, really complicated. This is a retired beam combiner, but it's just a simpler one where it brings in two beams, reflects the light off of these mirrors, puts it into optical fibers, causes it to interfere, and then back here there's a camera. So that's what all these optics, all these things do. And then that's where we get the data. And from that, we can make images, we can measure the diameters of stars, we can see spots on stars, we can measure some, I'll show you images we've created from this. Um, and then we have an operator, and I'll go introduce you to Norm. He will be operating tonight. This is the screen he sees. So you got to think all these things, all these subsystems. You have 6 telescopes. That's a lot to control. 12 adaptive optic systems. You got to monitor the sky. You got to monitor the weather. You got to monitor all the domes for the telescopes are moving, and then the instrument itself. Typically during the night, we have one operator and one scientist. Scientist is hopefully here in person, maybe here remote. Some of these can all be operated remotely, but we have an operator here for safety and to keep everything running on the telescopes. So these are GUIs, the graphical interfaces. This is one telescope's control. It's another telescope. Every one of these is one of the 6 telescopes. And then embedded in here are the AO systems. Over here are the servers that manage it, the stuff that controls the domes. This is weather monitoring, how to turn the power on and off, how the beams are sampled, the mirror covers. You can imagine if any of these things don't work, science doesn't happen. What's amazing to me is that how often this works. Every night, most of the night, we are getting data. If the weather is good, we are observing. So this is kind of what the operator sees. And I've said before, I can train someone to use the array and take data in a few weeks to a month. To troubleshoot it and fix it when something doesn't work is years, depending on what happens. That's where the real art kind of comes in. So this is a diagram of the whole system made for the other interferometer, the one in the southern hemisphere called VLTI. So ESO made this. The light coming from the star, here's your star. You think of it as just giving off this broad wave, just like a steady, flat wave coming at you. Hits this telescope, travels this distance, eventually hits this telescope, and this distance is what has to be delayed. They have a delay line, so they have carts that move back and forth here, and then they bring it to a camera, and then they get interferometry fringes. So this is the one slide of everything I showed you all the steps of. Okay, what does it look like? What is the science? I'm not going to go too much into this, but basically, the contrast of those squiggly lines, that's the light and dark. You can see here, light and dark bands. If you just slice across it, you'd see it's a peak and a valley and a peak and a valley. That's what we call a fringe. So that's the interference pattern. This is the constructive and destructive interference of the waves. If you look at the difference between the bright spot and the dark spot, we call that the contrast. So this one, you've got really high contrast. You've got big waves. This one, you have small waves. So you see, it's not as easy here to see the light and the dark bands. This is what happens when the star is very small. This is what happens when the star is very large. It changes the contrast of the fringes. Now we can plot that as a curve. And so based on the size of this curve, we can figure out if it's a small star or a big star. That's the first order of the simplest thing we can do with an interferometer. We can tell you if the star is big or small. And what we do is we look at another star that is very, very far away and very, very small. So a point source. And that's our ruler, right? And we compare that star to the science star that we don't know the size of. So we know one that is very too small to see, but we know it's bright, and it gives us our baseline for the baseline's another bad word to use because we use baseline in another context, but it gives us our base of our ruler, our starting point to measure from. So that's our calibrator. So we calibrate our interference pattern. And then we could say this star is, half a milliarcsecond big, or 3 milliarcseconds if it's a really big star. That's our first bit of science we can do. From there, it can start getting into the weeds. We can look at how this kind of curve bounces, and that'll tell us, well, is there darkening around the edge of the star, or is it a uniform disk? What model of star matches this? And then from there, we can get even more complicated. We can measure binary stars, two stars that are separated from each other. We can see how far away they are from each other. We can see their orbit if we observe them. We can combine it with spectral stuff from radial velocities, and we can actually start to put together a 3D orbit of stars going around each other. We can, if we have all of the telescopes trained on it, we can measure features on the surface of the star. So we can start seeing if there's a spot on the star or not. So that's the science we're doing. When I say, as mentioned in some of the advertisements for this, we're going to look at squiggly lines. So it's not very exciting. Hopefully we'll be taking data later and I'll show you, but it will be saying like, there's the fringes. We'll get really excited about the fringes. This is what I mean. These are the fringes. We're seeing the interference pattern. You're not going to see an image of the star right away. You have to reduce the data. We have to calibrate it. We have to do some math on it. But once you do this enough, you start saying, "Oh, those are really good fringes." And you'd be like, "Oh, that's definitely that's a an obvious, that's a calibrator. We can see the fringes really easy." And this is a kind of an illustration for like how you lay out your telescopes, what direction you've shaped them. So this is the Mona Lisa for reference, changes what details you're seeing. So there's how you place your telescopes, how you sample the fringes tells you a little bit about the structure. We call that the spatial resolution. So how far apart you put your telescopes and how close in tells you details you can see. So basically all you need to take from this is the orientation of your telescopes, where you place them and how far apart you put them contributes to your imaging. So there's ideal spots of where you want to place them. And that's what we do. That's why we have our telescopes are laid out in a Y configuration. So they make a big Y shape. So that's all the like in the weeds. That is your intro course to interferometry. Got another question, please.
Yes, yes, Scott. I'm sorry, Nick. This is just so incredibly thorough and detailed. I'm just amazed at all that has to go into making this work. It's incredible. Okay, so a question from Richard. Richard asks, so with your fringes, are you able to actually measure the distance to the star with those fringes?
We don't necessarily get the distance. There's other ways astronomers use to get distances. There's a whole lot of different ways astronomers get distances to stars. But what we measure is the angular diameter. So we can't tell you the exact distance and we can't tell you the exact diameter. We can tell you the angular diameter, how big it is on the sky. With the other astronomy, all the different sides of astronomy kind of all work together. From other types of astronomy, we get the distance. And with that, if you take a distance plus angular size, it gives you the actual diameter, right? When you look at something far away, it's really hard to tell, if I was looking at like a truck on the road, I can tell how big it is but I kind of know how big a truck is, so I can tell kind of how far away it is. But if it's an object you don't know the size of, say I see like a circle in the sky, is that a balloon? Is it a hot air balloon? Is it a small like helium balloon? Until I know the distance, I don't know the exact size, but the two things could have the same angular size. If it's close, so it's close to you and small, or big and far away, they're the same angular size. So there's two things you need. It's silly thing when people like report, in the camera like a UFO or something. A lot of the time it's a little tiny insect really close to their lens because it looks like a giant thing far away, but actually it's a small thing close to you. So we don't directly get the distance, but the distance informs the info we get. Everything kind of stacks together. That's why it's so many different parts of astronomy are all really important. They all complement each other. Any other questions? Well, that's the crash course in everything you never wanted to know about interferometry.
This is a great crash course, Nick. No more questions right now in the chat. But
Great.
I do have a quick question before we move on. So
Sure.
perhaps there's another famous interferometer that people may be familiar with, and that's the Event Horizon Telescope, which
Yeah.
works in the same way. Is there, when we're thinking about the EHT and they're spread all over the world,
Mhm.
uh, when it comes to the quality of the images that
Sure.
you can get, is there a benefit to being more spread out
Sure.
versus closer, like CHARA?
Gotcha. That's a great question. So the EHT, the Event Horizon Telescope, you may have seen this beautiful image that exactly matched what the predictions of the theory, which is always really fun. It's nice to know that you're not doing the wrong thing your whole career, which happens with science sometimes. That worked in radio. So light has lots of different wavelengths. So there's visible, there's infrared, there's X-ray, there's gamma, there's microwaves that you use to heat up your food. All of that is light. It's all the same thing. Now, the wavelength can change the type of technology you need to measure it or do science with it. Different detectors, like your camera, your digital camera, like on your phone and on your like if you have an SLR camera or whatever, they're actually really sensitive to visible and near infrared. If you want to do a fun thing, a lot of like your phone camera, if you take your TV remote and you press a button on your phone camera, you'll see it light up, but you won't see it with your eyes. That's because a phone camera is sensitive to the near infrared, but your eyes aren't. So you have different detectors that are sensitive to different things. So that's one aspect of it. One of the features of just quirks of physics, the way this works, that I said the resolution is dependent upon how big your mirror is. Well, I can tell you the full truth. It also matters what color of light, the wavelength of light you're looking at. So the shorter your wavelength, so the more toward the blue side, the better your resolution. And the longer your wavelength, more toward the red, or infrared, or even radio, the poorer the resolution is. The waves are bigger, the resolution is poor. So when you get to longer wavelengths, past infrared and into like submillimeter or microwave and radio, that Hanbury Brown and twist thing comes into effect, and you can start doing this thing called heterodyne. You can start doing this thing where you can combine the light without all these tubes and optics and mirrors. You can just record the signal digitally, encode a timestamp, and combine it electronically. We can't do that with the wavelengths we use. The small wavelengths, you can't do that. It's too high a frequency. It's too small wavelengths. Just the technology doesn't work. The physics doesn't work. With the long wavelengths, like the Event Horizon Telescope, the radio telescope, they had observatories all across the planet. The entire diameter of Earth became a big single aperture. However, they were able to resolve the black hole Event Horizon with that. However, we have the same resolution as the Event Horizon Telescope with our 300 meters. If you guys go from their wavelength down to our visible and near infrared, so much smaller, and that's entirely different due to the difference in the size of the light, the wavelength of the light. So different technologies, different things they can look at. Astronomers will look at the universe in all different wavebands because they tell us different things. Visible gets blocked by dust, but infrared will go through the dust and you can see the center of the galaxy. Radio will let you see, things like the actual black hole itself. You can go to all the way to like, 21 centimeters wavelength where you can look at the hydrogen, the unionized hydrogen of the universe. So there's not just, north and southern hemisphere, there's all these different types of science that you can do in astronomy based on the type of light you're looking at. So really, really great question. That's whole other fields of astronomy. The nice thing the radio can do is they can observe in cloudy weather and they can observe in daytime. We can't do that. But here at CHARA, we work in the visible and the near infrared, where we kind of have to combine the light like something Dr. Seuss designed of a whole lot of optical trombones and mirrors and vacuums and pipes and things that kind of are in some ways ridiculous, but work really, really well. So I wanted to introduce something that's new that we've just finished building at CHARA. This is called CMAP. It's the CHARA Michelson Array Pathfinder. This is a test bed for, and it's going to do its own science, a 1 meter telescope. We put it on a mobile stage, a mobile enclosure that we can move it around the mountain and plug it into different stations and run an optical fiber all the way to our delay lines and our cameras and our beam combiners and do science with this. So this is our first way we're going to expand the array to 600 meters and hopefully ultimately over a kilometer baseline. So I just want to show a little bit of how this thing works. It's this whole enclosure with a telescope inside. It kind of looks like a mushroom in this profile because it has to drive around our weird little narrow mountain roads. It is not street legal, but it is this telescope inside this enclosure that we can put at different places all over the mountain. So it's a really neat project, and we're hoping to get first science from it within a year. First fringes this year, hopefully, and science soon after. And this is what it looks like in testing. This is how we move it around the mountain. It mounts onto this platform here, this pier on these concrete pads. This is S2. So we're just expanding the array, whole new baselines, and this can be ultimately will be coupled into our other instruments. So it's really nice to see us doing something new here. This is the telescope inside with the dome open just after it was installed. This is kind of the CAD drawing. It's going to have this adaptive optic system on the side. The only difference is it doesn't go into the light pipes. It's going to go into fiber optics into the lab directly. And this is the three of them together. This is S2, S1, and CMAP. So this is above where they're going. So this is already out of date. We now have a concrete pad here, and we've put a pad here. So kind of reconfigure the array at will. It takes about an hour to move this thing and set it up. So one day, what we'd love to do is have pads all over the place and multiple telescopes and expand into the full Michelson array. Have 12 positions, 66 baselines. This would make this, premier interferometry facility in the world and just do all kinds of science. And as part of that, we'd also like to put in a 2-meter telescope, go even bigger. So that's kind of it for the how the array works. This is all our different instruments. And we mentioned Merkex and Mystic and Classic and Pavo and Spica and Cimaril. And this kind of tells you how faint it targets. If there's any amateur astronomers on here, we can see all the stars you can see by eye and then a good bit fainter. We've just had a test last week with Cimaril where we got to a H band, so the near infrared with Cimaril, to magnitude 10. So we're getting pretty faint for an interferometer. And this is just if you're curious what the kind of optics output looks like, don't worry about the details of this design, but basically all the light comes in and goes to this detector. So Cimaril is one of ours. I'll make Cyprian talk a little bit about what that is. Merkex, this is kind of what it looks like. You can see it's really complicated. You've got all the light going into fiber optics, going through a prism and more optics, and then you get fringes, and then you measure them on the detector. Mystic is very similar, but works in a different waveband. And you see these are what the fringes will look like. They share an optics bench. So this is the CAD drawing. That's kind of your guideline when you're installing one of these beam combiners. So it's all interesting stuff, very complicated, but very, very cool to work on. And Spica is another one. So we're getting brand new instruments, brand new beam combiners at CHARA. Chariot's one of the newer ones. This one is going to take fiber optics from the lab. So we're collaborating with people that do what's called photonics. So it's like electronics, but with light. So photonics, and astrophotonics, and giving a place for people to bring their new, that you can inscribe a full beam combiner on a piece of glass. And so that piece of glass has a little waveguide, little place for the light to go, and it combines it on the chip. So just like your electrons are combined and go through different circuits on your electronics, in photonics, your light goes through all these different channels and can do different operations. So what we've started to build here is a collaboration for people to bring their, different beam combiner that they get inscribed on a chip up to CHARA and test it with real starlight. So we've got new collaborations going on with that, working with people at Caltech, with the Leibniz Institute in Potsdam, and basically open to anyone in the community that wants to come and test this new idea or new instrument. There's nothing else in the world that lets you just come and plug in a beam combiner. So why do we care? Why do we build all this thing? Why do we do all this? The science part of CHARA are binary and multiple stars, young stellar objects, so places where planets may be forming, evolved stars, which are stars that are toward the end of their life, imaging the surfaces of stars, disks, cold debris disks around stars. So going to not just studying like a star as a point of light, but now we're in this golden era of astronomy where we have exoplanets. 1995, the first exoplanet was discovered. So it's in many of our lifetime. And before that, it was just hypothesized, like maybe there's other planets, maybe our solar system is entirely unique. We now know that there are more stars than there are grains of sand on Earth. And on average, there's an exoplanet per star. Some have many, some have none, but exoplanets are common. This was sci-fi when I was a kid. And now this is this golden era. Like when you think of like what hundreds of years now history books and science will look back on of like, wow, what a great time to be alive. Exoplanets is one of the ones here, as well as some of the other stuff like, looking at imaging black holes. So it's really an amazing time in astronomy. So exozodies are dust disks around other stars. So we're starting to look at stars as not just this like point of light, but it's a whole system where there's maybe a hot disk where planets are forming, or maybe an evolved system where the star is puffed up and starting to eat the planets that go around it, or dust and other debris, or comets, like exocomets have been detected. So it's really seeing it as a full unique system. So just to remind people who may not know, like stars come in all sizes. You know, our sun on this image is this couple pixels. Some stars are much, much larger than our sun. Some are as small as Jupiter. Um, we can measure the diameters of those stars. We do things like, look at the color of the star, the temperature of the star can tell you where it is in its evolution, how it will change over time, the fate of the star, or what's going on with the physics inside of it. All that comes from looking at the brightness of the star and the color of the star, and we can measure also the diameter of the star. And we've done that. So we have uh, scientist Ashley Elliott at Louisiana State University. She measured almost 700 stars, and this is that same, it's called an HR diagram, Hertzsprung-Russell. So going to the left is the hotter and bluer stars. Going to the right is the colder and redder stars. Our sun would fit right in here. And at the bottom are the really faint stars, and at the top are the really bright stars. So this would be really blue, hot, and bright, and this would be red, dim, and cold for a star. And this diagram here, what's neat about it, all these circles are actually measured diameters. So this isn't just like, oh, an illustration. We think we've measured almost 700 stars and getting the actual diameter of it. And that you could imagine knowing the diameter of something as well as its temperature and its luminosity, how bright it is, can really tell you a lot about the physics of how the star works. And we're able to do that. If you know the diameter of the star and the flux, the amount of light coming off of it, it'll tell you the temperature of the star. So this is fundamental astrophysics. This is about as basic as it gets in astrophysics of looking at the science of how stars work. So that's one of the main sciences we can do. These are images from the Kepler Space Telescope, and these are binary stars. The one way that our sun is kind of unusual, slightly, is that it's a single star. It doesn't have a companion. About when you go out at night and look at the sky, about half the stars you see are binaries. They're actually two stars going around each other. About a quarter of them are actually triple stars, and some of them are even more than triple. So looking at how these orbits going around each other, with how watching how stars orbit lets you with radial velocity and getting a full 3D orbit lets you measure the mass of the star. So this is how we weigh the stars, how we know how massive they are. When someone says the sun is this many tons, or some how many bananas the sun is, whatever unit that tries to make it something we can understand, because these are just big numbers, astronomical numbers. This is how it's done. We know the masses of stars by studying binaries. So as you can imagine, this is also really fundamental astrophysics. And it's also relevant for those exoplanets, because if you know the occurrence rate of the binaries, the occurrence rate of the exoplanets, if the star is a binary, you might be underestimating the exoplanet diameter. So this helps us actually measure, if you know the diameter of the star, one of the ways exoplanets are discovered is looking at the shadow that the exoplanet creates in front of the star, and that'll tell you the ratio of the planet to the star. But that doesn't tell you how big the planet is. Maybe it's a Jupiter, maybe it's an Earth. If you know the diameter of the star, you know that ratio, you know the diameter of the exoplanet. So with CHARA, with our ability to measure the diameter of the star accurately, you can then get, oh, that's an Earth-sized planet. This is one of the ways, if you see in the news, like another Earth mass planet of something this diameter is found, these are the ways it's done. Some star systems are really busy. Don't worry about all the words on this. What I want you to see is that this is Castor. Castor is a famous 6-star system. So it's not just a binary, it's a binary of binary of binaries. It is a 6-star system. And this is what astronomers look at when we say we get an orbit. These are measurements. These are the actual data of the components. So this is the orbit of this star going around this star, and this one is this star going around this star. So these are pairs of stars. These are the orbits. We can tell the orientation, the ellipticity, how circular it is versus an ellipse. And we have some instruments, some devices here at CHARA that measure this wobble. So this is a zoom in of this little bit of this orbit here, and you see the stars kind of doing a loop-de-loop. This is the wobble, and this is at 50 micro-arcseconds. So this is a really unbelievable like resolution. This is the kind of like really impressive science we're doing. Okay, the stuff that's a little more understandable. Images. This is an image of Zeta Andromeda. This is actually created from data. This isn't this isn't an artistic rendering. This isn't an impression or a guess. This is actual data rendered into what the star looks like. And notice it's got these giant spots going around. Just like this one, Lambda Andromeda has big spots. So our sun is actually right now in a really active stellar sunspot cycle. Those spots are tiny compared to this. These are massive, you know. And these other stars at different stages in their evolution, other types of stars, have these really big active magnetic fields and have these really giant star spots. Also, stars aren't solid. They're big balls of plasma that are rotating, some of them very rapidly. And if they don't have a solid, they're not like the Earth rotating, they can flow, they can change shape. If they're spinning very rapidly, they're going to bulge. And these are called rapid rotators. So we measure not just the diameter, but this, you can see the kind of darkening at the equator here. You can see the kind of darkening here. Because the stuff's being flung out because it's rotating, the stuff at the equator is further away from the hot core, it's cooler. So there's a temperature gradient across the surface of the star. So this is complicated, I know, but also this, you can see this is fundamental astrophysics. This is the shape of the star, this is the temperature apart, and you can feed this into the models and the theory and the doing the physics calculations and all the math of like, well, how do you get something that looks like this? Well, we take the physics equations and we can work it through and we can model the star. But we have these images that are created that give you a test on the model. In science, it's pretty easy to make a lot of different models. You have to check the model against reality, and that's what we're doing.
Nick, I have another question
Please.
here.
Yeah.
Which is just blowing my mind with all of this. When you're talking about the sunspots, the size of these sunspots, sorry, star spots actually,
Star spots. Yeah.
star spots, like this one on Lambda Andromeda.
Mhm.
We know on our sun, as you said, it's in a very active, solar maximum stage right now. Sunspots can be, like what's 20, 30 times the diameter of our planet. What size do these star spots get on like Lambda Andromeda? I'm
This,
just, they look huge.
yeah, these are, 20% of the size of the star. Our sun has never had a spot like this that we could, in any recent part of its history. I don't know about early in its development a billion years ago, billions of years ago, but this is, nothing like our sun. So that's the fundamental question. That's the part of the where it's interesting. What does this mean? What does this mean if you had an exoplanet around here? This would be a huge magnetic field. Sunspots, just recently we had a record-breaking aurora from a very active spot. If our sun developed a spot like this, there would be serious harms to life on Earth because this would probably go with a large magnetic field, a large stellar outflow. I would absolutely fry electronics and may affect life. Like, so these are questions that we don't know, and we can, start to wonder. We're getting, like I said, exoplanets, we're in this golden era. The question now is, well, are any like Earth? And can any have life? And to understand that, we need to know, just knowing the planet isn't enough. You need to know the whole environment. You could have stars that are much smaller than the sun and still have a exoplanet close to it. But then it would be tidally locked and it would be always facing the star. So then it would boil on one side and freeze on the other. Well, could you have life going around the horizon? We don't know yet. These are the questions that we're starting to be able to answer and hoping to be able to like image continents one day of an exoplanet or we're starting to be able to measure the composition of atmospheres of exoplanets. So could there be biomarkers? Could there be technomarkers? Could we see signs of technology? This is sci-fi 10, 20 years ago. Now it's near technology. We with the funding, we could build a telescope that would probably answer many of these questions.
Amazing.
We are not limited by the physics, we're limited by the funding. this one's really cool. So there's two different things on this slide. The top here is epsilon RJ. So this was a long-standing 100 years mystery in photometry. So looking, from Earth without this high resolution, you can measure the star, but you just see it getting brighter or fainter. When you can't resolve the surface of the star, you see it as a point and you can measure, oh, it's this bright today. Oh, it's this bright today. You look, that's a little dimmer today. And something is going on until things like CHARA and high angular resolution, you couldn't really tell, well, I know it's getting dimmer. I don't know why it's getting dimmer. So every 30 years, this star would get dim. And no one knew why. There were some guesses, there were some ideas of, okay, well, it's periodic, so maybe something must be orbiting it. But you could never find the thing that was orbiting it. What was orbiting it didn't give off any light. So with Brian Kloppenberg in 2010, created these images of Optical RJ, and you could see this dark kind of finger go across. And this is it all stretched out. This is kind of superimposed many images. And you see how big this disk is. This is an artist rendering of what's going on. Is you have two stars orbiting each other. This one we can see and the one we can't. But the one we can't is surrounded by a dust disk. And that dust is a big cloud that's blocking the light. So that's why no one else could see it. It was hidden from the amateur astronomers. It's hidden from professional astronomers. It's hidden by the dust. But you could see this shadow of it going around. So really just shows you kind of immediate benefit of the imaging. Another one really cool. And if Gail's still in the call, this is her paper. Great Nature paper, one of my favorites to ever be a part of. I was one of the operators here at CHARA for Nova Del in 2013. So this was a nova. This was a thermonuclear explosion on a white dwarf star. So it's a binary star. Matter from the evolved star gets kind of siphoned off and lands on this white dwarf around it. Eventually, enough of this hydrogen piles up that it hits this critical mass where it gets a runaway thermonuclear explosion, and boom, you get a bright star. It's called a nova. Nova means new. You could go outside, look up, there's a new star in the sky. The star was always there, but it was too faint to see. It gets so bright, you could walk outside and be like, that wasn't there yesterday. We are expecting anytime this year another nova. Jamika and I have talked. Ryan Norris is one of the astronomers that's got a proposal in to use CHARA. If this happens again, we're going to look at it with CHARA. In 2013, this happened. We looked at it with CHARA. This is this beautiful plot. This is the imaging. You see, it's exactly what you'd expect. I said a thermonuclear explosion. It's a fireball getting bigger. That's what this is. This is a plot of the brightness of this. And you're going to get into the astronomy side. You get like dust disk created and this other changes and how it's expanding. You could really did dive into the physics of it. But really the cool thing is 3 days, 5 days, 7 days, I was one of the operators. We were writing down the visibility, the contrast of those fringes, how well we could see the fringes on the whiteboard. And you could see in the raw data without even reducing it, without doing any of the fancy math and all the stuff we have to do as astronomers that we get nerd out about. You could just see that this is a bright object getting bigger, and it's a fireball. So really cool paper. And we see where the dust starts to form around it as it cools, as it gets further away from the star. So really looking forward to whenever this happens. We have what's called a target of opportunity. So you can kind of put in a placeholder proposal, but like, hey, when there's a chance, I want to look at this. Here's the science behind it. To use telescope time, there's a whole ranking system. You write, you ask, you beg, you say why you want to use a telescope, and then a panel of other astronomers, which you also may serve on for other people, looks at it, grades it, and says, okay, your scores are good enough. I always think of like, gymnasts in the Olympics, 9.5, 9.4, 7.8. Average those scores, you figure out like, yes, we like your project. We think it has scientific merit. We think it's technically possible. You get 2 days or 3 hours that you can try and observe it. And if the weather's bad, bad luck, you try it again next semester. But that's what it is as an astronomer. It's highly competitive, but really looking forward to hopefully good weather and this happening at some point this year. This is, I talked about giant stars and the surface of stars. This is, I don't know why there's a line there. This is a computer model. This is based on the physics, hydrodynamic, simulations of the surface of a very big star. I don't know if this one's Betelgeuse or not. I don't recall. This is another model simulation. this is the image. So this is Ryan, the guy that's going to do the nova observation with us, hopefully. This is his image of this star, called AZ Sig. So it's a very massive star that, if it was in our solar system, the surface of the star would go all the way out to Jupiter. So thankfully, our sun is much, much smaller and will not reach out that far. But this is the image of that, and this is the model. And you see, I believe this model looks like it's pretty accurate to what I see here. So you can check your physics and see. And the more baselines you have, the more telescopes you have, the better resolution you have, the better you can make this image, the better you can compare it to your model, the better you can figure out the new physics part behind it. This is what, the surface of like something like Betelgeuse probably looks like. It's these huge cells of convective matter going up and down and changing temperature. It's kind of like a boiling. Very different than our nice, stable, cool, sun. Astronomy will, if you have existential crises and fears, astronomy is not the science for you. You'll start thinking of all the different ways the universe can kill you. Very thankful that this is not our sun.
Nick, real
Yep,
quick, back
sure.
to that previous slide, which is just blowing my mind here, just to imagine that that's happening, on the star. And as you said, this is not happening with our lovely, quiet, stable sun that we all know and love. Now, is that because our sun is still a main sequence star, and this is a more
Yep.
evolved star?
Exactly it. It's a main sequence star. It's still in its prime of its life. It's also a lower mass star than these high mass stars. So the rule with stars is they kind of range from these red dwarfs, which are like candles. They light up and they just burn steady with no surprises for a trillion years. There's the middle stars like our sun, which have a nice birth, settle down into a nice picket fence, boring life with no surprises until they puff up at the end and become a nice, pretty nebula. And then you have these really massive stars, which instead of lasting like 10 billion years like our sun will, their lifespan is in the millions of years, so 1,000 times less. And they just have so much mass. They have so much energy in their core that they are just running through the periodic table, fusing all these elements and just fusing and fusing and fusing. And they can puff up and create these giant explosions that create supernovas, that create black holes. So basically, the equivalent would be for a human, if you knew the weight of the baby, you could tell its lifespan. It's real weird. For a star, the big babies, the big stars, burn out and die real young. The scrawny ones that just putter on live for 1,000 years, and the middle ones live, normal 70 years. It's a real strange thing of astronomy, but it's nice that it's both complicated and simple physics. That if you know the mass of a star when it first turns on, you can pretty much predict its future.
Incredible.
It's a
Ah,
bonfire versus a candle.
that's a great analogy, Nick. Um, wow. And so now Jim has another question. So he says, I
Sure.
assume that movie of Beetlejuice, I'm not sure if we know if that's
This one,
Beetlejuice or
yeah.
not,
Yeah, I
that one.
remember, yeah.
We'll call it that.
Yeah.
Assume that movie of Beetlejuice is time compressed. So
Yes.
what would the actual time scale of these pulsations be? Hours, days, years?
This movie you actually can see right here, it's clicking off maybe a tenth of a year per second. So you would see changes over the course of the year, but nothing this fast. This thing goes through, I think the full loop of 30 seconds goes through about 3-4 years. So not as fast
Okay.
as you're seeing here, but it's also the size of the orbit of Jupiter. So just the time scale for things that far out to move is going to be slower. But on astronomical scales, this is a blink of an eye. This is nothing. We think of things in terms of giga years. I'm going to go a little bit quicker through, let's skip the last one. This is another one of these mysteries of something getting dimmer. This is a recent paper from Narcy, one of our employees here at the array, really valuable at the array. These are the images. This is a star, which you may have heard on the news like last year, the great dimming of Betelgeuse. That Betelgeuse suddenly got really dim and everyone freaking out of maybe it's going to go supernova. Well, it's not the only one to do that. This star, RW Ceph, had the similar thing. It's called a dimming event. And what's thought to have happened is that it had an ejection of matter. That matter flew off toward Earth and still very far away, never going to hit us or anything like that, but in our line of sight. And then as it got away from the star, it cooled, making a dust cloud. And so it caused the star to rapidly get dimmer by a full more than a magnitude. So that's really, really faint, big change for an astronomy point of view. So we were able to image the star during this faintest stage and then the rebrightening. So just cool, modern, recent science. I'm going to hit one more thing on the science, and then I want to walk through I think it's dark enough now that Norm may have the telescopes on something and we can take a look. Nora Ibrahim is actually one of the scientists observing tonight. This is her paper on this luminous star, and she imaged this disk. The star's in the center here. This is done with Mercax. The star's in the center here, and this is a a gas disk of this young stellar object viewed almost face on. So looking directly kind of down the pole at this ring, it actually does have a ring around it. And she noticed this bright spot, and this over about a month, it rotated in the image. So this bright object is a rotating feature that's real. It's not an artifact of creating these images, and it may be a planet forming. So really, really cool science. Yeah, Nora's fantastic to work with. Unfortunately, she's remote, so I don't know if we can pull her in on the Zoom. I can't just hand my laptop to her, but just really exciting science that we're doing here. I'm going to skip through some things. We hope to one day, image an exoplanet during transit. With a little bit of work, it's possible. There's 250 known exoplanets with host stars that CHARA can look at. And with the right baseline and the right sensitivity, it's possible we could actually resolve this transit. And then I'm going to stop with the last thing. This is a galaxy. This is one of the nearby galaxies, very famous. England does extra galactic astronomy, NGC 4151. And one of our collaborators, Kishimoto, at Kyoto University in Japan, will use CHARA to measure the diameter here of this innermost dusty region and show that it's perpendicular to the jet coming off this active galactic nuclei. So an active galactic nuclei is the core, the black hole at the core of another galaxy that's feeding. Not like our galaxy that has a black hole, but it's nice and quiescent. It's not eating anything right now. Some of these galaxies that matter, stars, are falling into the black hole. That matter hits the accretion disk, creates huge amounts of energy, huge amounts of light. A lot of that gets put off in these jets that span, the length of the galaxy, but going off perpendicular to it in the north and the south of it. This region here, we find that it's actually not aligned the same way as the disk. That tells us something that's a mystery. Like why isn't it lined up? So that's one of my favorite phrases of science, and isn't eureka? It's that's funny. That's how a lot of it is. Like, I thought it worked like this. I measured something, it doesn't work like that. That's funny. Why? And having the curiosity go through. And so this is where actually one of our pushes, this is how bright that galactic source is. With our new instrument, Cimaril, these are how many of these AGN we're hoping to be able to measure. So we can only reach this one. We're right at the edge of being sensitive enough to really get a lot more targets. And so you always want to go a little further. So with that, I think I'll stop with the slideshow and I'm going to walk around and make some other people talk. And if we have time after, we'll go through and have some questions. So let me turn on, oh, there's my video. Give me 1 second. I still mask when I go anywhere. So this is my messy office. We're in this control room. Wave. So this is our operator station. There's Norm, our operator.
Hello.
Can you hear me okay, Jamika? And can you hear Norm okay?
Yes, we can hear you both just fine.
Great. So Norm, you want to say, have you locked on a star? What you doing?
We did. We locked on our first star. It's a fringe finder. It will provide very easy fringes, hopefully, to get us the offset so we know where to get the carts. And then we will go to the science after that.
Point out the fiber map.
So the combiners that we're using are the fiber fed combiners. And so a raster scan is done where it just goes back and forth, finds the peak of the flux, and then moves the fiber holder to try to put the fiber tip right where the peak flux is. So we can see the map just finished. It will move, and our flux trend plot here shows us whether we've made an improvement with raising the flux over what we had before. So it's still early in the night, so we're getting some refining done, getting the AO systems working correctly and stuff like that. So we make little tweaks as we see certain things are falling behind others. We try to get all the systems operating to the point of where everything is as matched as possible.
So this is the telescope AO, this is the lab AO, this is the star here with the beacon turned on, so we can speed the system. So all this, and this, like Norm said, this is getting the light from the star onto the imaging of the optical fiber in the lab. So think of getting all that starlight, goes to the telescope, and then gets a fiber that's, you know, less than the diameter of your hair. So Norm has the fun of playing the most tedious video game you could imagine.
And here's some fringes.
Yeah.
So the nice thing about a fringe finder is it gives very easy fringes. It helps you confirm that all your systems are good, that your metrology is good, that the carts are in the right place. And once you have the fringes, then you start to go to the more difficult things, getting fringes on your calibrator, which shouldn't be too hard, and your science, which depending on how challenging an object it is, can be quite difficult. Sometimes certain fringes are there and others aren't, depending on the baselines and the orientations, things like that. So the
And I
fringe
can-
finder, though, should just be real easy. It gets everything, confirms that everything is working.
And while we're getting fringes, I can share that GUI on my screen if we want to go into more detail of it. And I'll walk over here. We have another control room. This is our secondary room. We have Myra in here.
Hi.
She's visiting from Michigan. She was doing some upgrades on the Merc-X combiner. You want to say a little bit what you did?
Yeah, so I guess this week I installed a filter wheel in front of Merc-X, so that holds different optics. And the way we used to do it is like somebody would have to manually put an optic in between, you know, the light and the camera. But hopefully with this filter wheel, it's all automated, so people can do it remotely. So I hope that will help.
Yep.
Yeah,
Thanks a lot.
no problem.
So we can have multiple beam combiners running at once. And so we could have people stationed here and someone in the main room and do different science or engineering with some telescopes all at the same time. All right. That is my crash course in CHARA. And then if there's any questions, now's a great time. And I'm going to see if I can pull up the GUI that Norm was using.
Thank you for that fantastic tour, Nick. That was amazing to be able to see now that you've given us this crash course, to see things in action there. Yes. Now,
So this
before-
is, yep. Go ahead.
Oh, sorry. Before you dive into what this is, is Norm the only one there
No.
running things?
So we have 3 different people that work as operators. We have Norm, Ollie, and Becky. And so
Oh,
they
okay.
trade off. They do a few nights and then trade.
I see. Okay.
But only one at a time. So it's typically, like I said, one operator, one scientist, sometimes more. You can kind of see fringes coming in here. So this is a plot where it's the wavelength up and down, and then the fringes go across left and right. And you see it. So like I said, squiggly lines, it's not going to look impressive. But now you see we go all the way from how bright and faint those squiggly lines are. So it's as if, when you drop a rock in a pond, you get ripples going out. And if you drop 2 rocks, the ripples go out and they cross over each other and sometimes constructively interfere and sometimes destructively interfere. It's as like we look at those constructive and destructive interference and tell you the size of the rock that dropped in the pond. Like it's a weird, like you wouldn't think it would work, but it does. And it's always when people come and visit without the background, they come and they're a little disappointed, like, we want to see what you're looking at. And it's like, well, there's not an eyepiece, there's not a sudden pretty picture of Saturn on it. But for interferometrists, this is really exciting. And hopefully for you guys too, now you can see with doing this and doing this very well and very carefully, we can create those images that are just would otherwise be completely impossible.
So from these fringes, Nick, how do we go from these fringes to those incredible images that you showed us? Now I know there's a lot that goes in there, but into it, and it's an incredible amount of work. But could you give us just a brief insight into that
Sure.
process?
Math, a lot of math. Specifically Fourier transforms. Some people may have worked with audio, understand like Fourier filtering. It's a way of changing something from spatial resolution and frequency space and back and forth. And so you're looking at spatial frequency. There's a good XKCD comic where he talks about, oh, I accidentally took the Fourier transform of my cat. And it's a plot with like a really high on one side and then drops down. And it's because the small details are high spatial frequency. The low frequency are the big things, like the shape, the diameter of something is a low. I mean, it's for an object, the lowest thing is its diameter. It's the same type of math and computer programming that works between, like, if you ever use like the blur feature on a image editing app like Photoshop. If you blur something, you're removing the high frequency information. So for us, the high frequency information comes from the long baselines, the low frequency information comes from the short baselines. And if you have enough of those different slices of frequency, you can combine it and you're working up a whole image from the hair on the cat to the shape of its head, right? So for the star, you get the high resolution from the long baseline that gives you like the spots on the star. And you can also look at what we do is I talked about like there's triangles. By combining 3 telescopes, it tells you something about the symmetry. So is it symmetric or not? So we've got resolution of the spatial resolution of to make an image, and then we have how symmetric it is. So like that thing of the disk and whether it's round or not, we get that. So it's all in combining these different slices. Your eye does a Fourier transform, the telescope does a Fourier transform automatically. When you look through a telescope, it's doing a Fourier transform. It's a optical mechanical thing where it is essentially doing the mathematical operation of a Fourier transform. You just don't know it. It's all happening in the background, happening in your brain, just happening in physics. We have to do it, manually through computer code, to create the image. But it's the same principle, same idea.
Amazing. Okay, let's see. Okay, Rob, no problem.
I see a clock counting down. Do we have more than 2 minutes left, or is that our Zoom session's going to get?
Oh,
or is that a rough guide?
Really? There's a clock? I don't see a clock. Okay.
Oh.
Yeah.
Oh, it's just the scheduled meeting. We're just going over our scheduled time.
Yeah,
That's okay.
no worries. It shouldn't cut us off. Yes, we'll stay here until we've answered everyone's questions. So let me just enable video and audio for everyone. Okay, so if you'd like to unmute yourself and or turn on your video, you can, so that we can maybe take these last few minutes to interact directly with Nick. And if we could maybe start off with those in the CHARA conference room. I believe Cyprian is in there.
Cyprian, say something.
If you'd like, Cyprian.
Are we unmuted now?
Yes, now you are.
Yay. Right. Sorry, so you were saying, Nick?
I got a quick question you can answer, people. Why do you have a whole bunch of champagne bottles behind you?
Yeah, so those are all the achievements that you have done at CHARA. Every time you have a big achievement, we put the champagne to
So they're all signed. They all have whatever feature of the night, the new record, the new beam combiner.
Yeah, everything, something new is working, basically, and something interesting is happening. Yeah, we get a bottle of them. And yeah, all the teams that participate to signing the bottle, so that you have just a witness of all the years that that we have.
But drinking is optional in astronomy.
Mhm.
Well,
So-
Yeah, it's optional. Everyone does it.
Nights are very long,
Yeah.
and
go.
time to celebrate. We usually have more things going wrong than going right, so it's important for morale to celebrate.
I love that. So Cyprian, could you maybe give us maybe an introduction to what it is that you do at CHARA?
Okay, yeah, so I'm the visitor support scientist. So basically I interact with everyone outside of the CHARA community, the CHARA consortium. So astronomers that want to use CHARA, to help them to propose, get a proposal ready so they can ask for time with the correct instruments to do their science, depending on what they want to do. Observe for them or teach them how to observe if they want to observe themselves, which we try to push a lot. Also reducing the data and analyze them. So once you have your data reduced and everything, what does that mean? Some people don't know interferometry, so they don't know how to interpret the data. So we help them as well. So that's one part of my job. The other part is I work on the Silmaril instrument that we are building. And so, yeah, just building a new instrument and doing science with the instrument that we have. So that's what I do.
It's really nice. Like even astronomers, many of them don't know interferometry. So we are open for anyone. If you have a science case, they can apply, and we will help them with getting their data, help them reduce it, help them interpret all of that. So even astronomers that don't know interferometry are always welcome to use the array.
Amazing. Was that Bryce? Were you raising your hand?
Oh, sorry. Scratching my head.
Oh, I thought you were raising your hand to introduce yourself as one of our former hosts, our first NASA Infrared Telescope Facility session. And we'll be having more sessions with you that we're looking forward to later this semester. Maybe you could give us a quick intro.
Sure. My name is Bryce Bull, and I am what you call a postdoctoral researcher at NASA Goddard Space Flight Center. I study asteroids and comets of the solar system. I study things in our solar system, and I think this stuff is really cool too. Although I'm a big fan of asteroids and comets, of course, being able to resolve the surface of a star and do compute orbits of stars around other stars is pretty fascinating to me.
Absolutely. I agree. It is really incredible to see this intersection between, or at least with Shadow the Scientist sessions, with our astronomy sessions, we get to really see how the different aspects of astronomy and astrophysics can support each other, and how it provides insights that can be used in slightly different ways to help, like with interferometry, for example. And I look forward to being able to share more of this with our audience. And let's see, we also have at the table Laura May Abram. Laura May also was one of our hosts in that NASA Infrared Telescope Facility first session. Laura May, would you like to give a quick intro?
I'm here as a tourist tonight mostly, but I work at Griffith Observatory. Did a lot of science communication these years and a lot of telescope things, and getting back into academia now. And interferometry is amazing, honestly. I feel like Matt Wilson especially, just everything here, people don't necessarily realize. I always tell people in LA, that this facility exists here, and that, yeah, the array is here. And even though the 100-inch is not used for research anymore, just an amazing facility. And yeah, interferometry is amazing. All this star spot stuff is so cool, and I hope that that we can continue, that we can expand it, because that's really awesome.
I agree. It is really awesome. And maybe Nick can close us out by maybe talking about that event that is hopefully going to happen any time now.
Yeah, that'll be another nova. It's predicted based on these things are periodic. They happen so often, and it's known from looking at the light curves. But whenever it does happen, we have the time allocated. So to get time at a telescope, you write a proposal, it goes get reviewed, and this one is there and ready as a placeholder, and it's expected anytime. That will be a really exciting time, and we will probably be releasing like press releases and stuff on Facebook and doing a Shadow of the Scientist, at least one. So it'd be very nice.
Well, Nick, Cyprian, Gail, Bryce, Laura May, I know I think I speak for everyone, and we've had great comments in the chat. And Richard here is saying, amazing what can be done with the light of a star. It's like the DNA of a star. And really, really, that's great insight. And we've had a lot of thank yous. This was amazing presentations in the chat to everyone, and also direct messages to me. So this went really well. This is very
Happy to
informative,
do it.
incredibly engaging, and we look forward to our next session with you, Nick, Cyprian, Gail. Thank you so much for welcoming us into CHARA. And I have to say, I'm really excited to be there in person next week.
I'm so excited.
I'm thrilled to get an in-person tour and to meet you in person, Gail, Cyprian, everyone, and I'll see you also next week, Laura May. And here we have Gail. Gail, please
Gail, you want to say something?
join us.
Oh, hi. I'm Gail Schaefer. I'm the director of the array. I'll keep it short and just say that, yeah, working at CHARA is really great because I get to work with this talented staff who keeps all these optics aligned and working. And yeah, good to see you all.
Thank you so much, Gail. We are so grateful to you for you all for your collaboration with us with Shadow the Scientist, and look forward to having more sessions with you. And for everyone who joined us in the audience, again, my name is Jamika Marshall. I am the coordinator for the Shadow the Scientist initiative. It has been an absolute pleasure to have you with us for this, our very first session featuring the scientists and the amazing science from the CHARA Array. We look forward to having you in future sessions. If you're on our mailing list, you can look for our emails anytime in your inbox. And if you are not already on our mailing list, you can respond to your confirmation email to send a request to me to add you to our mailing list. In the meantime, have a great rest of your morning, afternoon, or evening, and we look forward to seeing you all in a future Shadow the Scientist session. To Bryce and Laura May, I hope you have a great rest of your time there visiting with Nick and Cyprian and Gail at CHARA, and I'll hope to see you all next week. Thank you so much. Aloha.
Thank you, Jamika.
Aloha.